Good day, dear friends. My name is Evgeny Proskrin. I'm the founder of ATF Group. This is an engineering and manufacturing group of companies that started in a garage, producing hardware for transformers. And now it offers digital solutions for a wide range of industrial sectors. Today we are launching a series of micro lessons to share practical knowledge and help our energy sector operate more reliably, efficiently, and safely. After all, our mission is simple: your energy under our protection. Power transformers are not just components in a power grid. They are machines where energy constantly flows, and as a result, heat is inevitably generated. Today we begin the first chapter and focus on the fundamentals: where this heat comes from, why cooling is critical, and how oil helps preserve the life of the equipment. This module covers energy losses, heat generation, transformer oil as a coolant, and temperature limits defined by international standards. Heat in a transformer appears due to two main types of losses. First, snow load losses caused by magnetic processes in the steel core. Even when there's no load, the magnetic circuit consumes power and produces heat. Second, load losses, also known as short circuit losses, arise when current flows through the windings. The higher the current, the more heat is generated. This follows the Joule-Lenz law. Heat increases in proportion to the square of the current, the resistance of the conductor, and the duration of current flow. So, a transformer is a device that inevitably loses part of its energy as heat. If this heat isn't removed, insulation ages faster, metal components deform, and the entire system may fail. In most power transformers, mineral insulating oil is used. It performs two key functions. It provides electrical insulation between windings and other internal parts, and it removes heat from the active parts, the windings and the magnetic core. Oil circulation can be natural, driven by the difference in density between hot and cold oil, as in Onan systems, or forced using pumps, as in OFAF or OFWF systems. The critical properties of transformer oil include flash point, which must not be lower than 135 to 140 degrees Celsius, viscosity, which affects the circulation rate, and thermal capacity and conductivity. The higher they are, the better the cooling. The oil must also resist aging and oxidation and contain no water, otherwise it loses its dielectric strength. According to international standards such as IEC 60076, certain temperature limits must not be exceeded. The oil temperature in the top layers must stay below 95 degrees Celsius during normal operation. The hotspot temperature in the windings must not exceed 120 degrees Celsius. Depending on the insulation material, the limits vary. Class A, from 105 to 110 degrees Celsius. Class B, up to 130, and Class H, up to 180. Exceeding these limits rapidly accelerates insulation aging. For example, every 6 to 8 degrees of temperature rise cuts the insulation's service life in half. To prevent overheating, transformers are equipped with oil thermometers, temperature indicators, and winding thermal sensors, especially in modern models. Signals from these devices are sent to control systems. They activate fans or pumps when set thresholds are reached. Additionally, transformer oil is regularly tested in laboratories to measure dielectric strength, acid number, and water content. These values indicate how much the oil has aged. Now let's take a practical example. Suppose we have a 100 megavolt ampere transformer with natural cooling. Under a load of 90 megavolt amperes, the oil temperature in the top layer reads 82 degrees Celsius. Is that acceptable? Yes, it is. But if the load increases further, the cooling system may become insufficient. If the oil reaches 100 degrees, either the load must be reduced or the fan switched on. And if the windings reach 120 degrees Celsius, the transformer must be unloaded immediately. Now imagine this. You're operating a transformer with oil insulation. The oil temperature is 92 degrees and the ambient temperature is 35 degrees Celsius. What would you do? Would you switch on the fans, reduce the load, or is this within safe limits? Think it over and share your answers in the comments. Today we covered 3 key aspects of efficient transformer cooling: where heat comes from and why it's inevitable, how oil helps to remove it, and which temperature thresholds must not be crossed. In the next video, we'll go further into the subject of cooling. We'll look at the components that make cooling possible: radiators, fans, pumps, and heat exchange systems. Want to explore the topic in more depth? Visit our website. The link is in the description. Interested in real-world solutions and industry challenges on this topic? Contact us. Our details are on the screen. Want to become a part of the global energy flow? Reach out to us. You'll find our contacts on the screen.